No, this doesn't actually match your data at all. This is just data we just threw in there. Okay, so first of all, do the concentrations match?
Yes.
240, 240, 240, 360, okay? So what did you get for the reaction time for experiment 1?
32.
32. And number 2?
74.
34. Number 3?
74.
74.
No. For the second one, it's 74.
74.
That one is 108.
108.
62.
2.
47.
47.
45.
45. All right. So basically what we have here is our reaction time. Quick reminder that your reaction rate is going to be per second. So it's going to be something per second. So reaction time is going to be in seconds. Reaction rate is going to be the inverse of that. So there's your reaction rates. And that's the information we care about. So far so good?
How do you?
Now I'm going to show you some crazy math you can use if you want to. If you like math, you can do the math thing. I like just looking at it because honestly, if I'm doing this in an AP class or an AP test where I'm timed, I'm realizing that it's going to take me more time to do a bunch of exotic logarithms than just look at it. And if I looked at these, which experiments are going to be the most useful to determine the concentration of our thiosulfate?
Probably 4 and 5.
4 and 5?
Or to do the which?
For we're going to determine the
Oh.
we're going to determine the order. Sorry, the order of the thiosulfate.
So then
1 and 2.
1 and 2. Okay. So the hydrochloric acid is held constant. 1 and 2. What happens in the change?
it's half.
It's halved. And what happened to the time?
It doubled.
Yeah, doubled. And the reaction rate is
1/3.
ish. So 1/2 is pretty good. So it's getting there to 1/2. 1/2 to 1/3. Okay. So that seems to suggest that the thiosulfate order is what? First order. Okay. So you have you double here, you about double here, about. So to confirm that, okay, does that make sense first of all? Okay. I'm gonna throw some math at you in a little bit, but right now just look at that and just like, okay, this is what it is. If you have extra time, you can do the math, and if I get a green pen that works, I get a good math too. All right, so let's look at another one. We have another piece of data that allows us to look at the order of the thiosulfate. What's that other piece of data? 1 and
3.
1 and 3. So in 1 and 3, what's happening to the rate? So what happening to the concentration?
It's 1/3.
It's a third as much. And what's happening to the reaction time?
3 times as much.
3 times as much. And what's happening to the reaction rate?
Oh, it's 3 times.
Yeah, third as much. So it appears that it is first order because what we did to the reaction concentration, we did to the thiosulfate concentration, we also did to the rate. So it appears to be first order. Do you agree with me?
Yes.
Okay. So if this makes sense to you, give me a thumbs up.
But
If you'd like me to go over it again,
yeah,
yeah.
hypothetical.
Uh-huh.
So let's just say like if you took 1 and 2, and so the time doubled, but then or the reaction time doubled, but then if the or no if never mind.
If you double the concentration, it quadruples the reaction time,
Yes,
then it would be second order.
Okay, that's enough.
Yeah. If what you do to the concentration also happens to the rate, first order. If what you do to the concentration doesn't affect the rate, zeroth order. And if what you do to the concentration happens to the rate twice, second order. And if what you do to the concentration happens to the rate 3 times, third order.
Okay.
Okay. So are we good with thiosulfate being first order?
Yeah.
All right, let's take a look at hydrochloric acid. What would you use to determine the order of the hydrochloric acid? What experiments?
4 and 5.
4 and 5. Okay, so 4 and 5, what's happening to the concentration? So we're doubling it from 5 to 4. And what's happening to the time? About 1.3. It's about 1.3, 1.4-ish. So that gives us a reaction rate that's about 1.4-ish. Okay. Can you see that?
Mm-hmm.
About 1.4. Right.
So is it like the order would be a little bit less than 1, or?
Right. It basically would suggest that it would be a little Okay, so in this case, we are increasing the concentration and we're slightly increasing the rate. So a little bit more than 1. I'm sorry, a little bit more than the same, if you will. Okay, and then in here, from 1.2 to 360, what's happening to the concentration? It's about 3 times as much, and this is still about 1.4 times as much. Strange. And this is still about 1.4 times as much.
It's 0.
Yeah. So I would jump out and say it's probably 0th order. We're gonna throw some math at it to confirm that it is. But if I was doing this on an AP Chem test, I would call it 0 order and then call it good. Just move on. I wouldn't take the time to do all the math, simply because it's a time test. Does that make sense? Okay. Do you want to see the math?
Yes.
Sure.
Okay. I know Cameron's like, I'm gonna do it. It's Cameron's been doing it. All right. So the math. All right. Here's the math. Calculate order with the rate of one over the rate of the other. So basically, you write the entire rate law of one. Yeah. Sorry about that. It's black on blue. Yay. If you're in the front row or you have binoculars, you can see it. Basically, you set the entire rate of 1 over the entire rate of 2. So you take experiment 1, its entire rate law, put experiment 1's entire rate law over experiment 2's entire rate law. Assume these concentrations are constant, which they are, so they cancel out. It's like 2.4 and 2.4, boop, they fall out. Make sense? Okay. So what you're left with is rate of experiment 1 equals a concentration of the thiocyanate 1, experiment 1. Rate of experiment 2 equals the thiocyanate concentration 2. Plug the numbers in, and now you're solving for n. Okay. Again, if you are solving for an exponent, how do you solve for an exponent?
Logarithm.
The logarithm. Yeah. You isolate the exponent with a logarithm. You take a logarithm of this side, logarithm of that side, so it's a logarithm of 0.315 over 0.0098 equals n times the logarithm of what's inside. Remember logarithms? No, like I hate logarithms. So when you take a logarithm of something, you move the exponent into the whatever that position is called. We'll call the front of the log. So when you take a log of something, you move it to the front. And then you look at it and it says, okay, I took the logarithms, n is 1.68, so that rounds to 2. Okay. Would you like to actually try it with your data? No? Okay. Well, anyway, if you're curious, there it is. It's also all over the web. But again, practically speaking, if I was doing this on an AP test, I would use the data, I'd make some conclusions, and then move on. Capiche? Cool. All right. Camry wants to be in that 5%. She wants to be in the 5% of the 5s, the highest 5%. So I'm going to do it. Okay, so there we go. So now we've established that the rate law is, or the rate equation, rate equals K, HCl is 0th order, and the S2O3, 2 minus, is first order. Cool? What does this tell us, practically speaking? Go ahead.
It doesn't matter how much HCl you have, so it's the same.
Yeah, as long as you've satisfied the stoichiometry and it's there to work with, it doesn't matter if you change the concentration, as long as you have enough. Cool? Okay. Now okay, does that make sense first of all? How do you solve for the units of K?
You see how many M's are there, and then you do 1 over S something to cancel the M's.
Exactly. So this is going to be molarity per second raised to the 0th order. And this is going to be molarity per second raised to the first order. And right away you're like, oh, that has an overall order of 1. This is going to be molarity per second. So if it has an overall order of 1, how many m's are in the denominator?
0.
0.
So just-
Yeah. Take away 1 and drop it into the denominator. So 0. So this is just molarity per second equals something. This is 1. This is molarity per second. And this has to be something. So it's just
I wrote it down somewhere. Ugh.
Yeah, I think it's just
S. Sorry, this is molarity per second. Right. This is just molarity. So this is just molarity, 1 over seconds. Yeah, sorry, 1 over seconds. How do you let it go so long putting molarity per second in there? 1 over seconds. Yes.
So for this particular reaction, why does HCl not, like the concentration not affect the reaction time? Like, is it too much energy or?
I don't know. I don't know. I don't. I'm a generalist. I don't know why that is. If I had to guess, and it's only a guess, is that there is plenty of hydronium ions, H pluses, in the solution. There are plenty of them. They have enough energy to react. They're just a proton. Acids very rarely control rate because you have a proton. It doesn't matter how you hit a proton. It's a tiny dot. The orientation doesn't play much of a role. But that's just a guess. So we don't know for sure. Again, people probably specialized it and they probably did the computer simulation and know exactly why, but I'm just guessing because there's so much of it and it's just a tiny little sphere, you can think of a sphere, that it's not going to control the rate. Yeah, I still got to print new ones of those. New one still leaks.
Do it.
Leaky tornado, go! Leaky tornado!
There you go.
Yes, it's a very leaky tornado.
Don't you get like just
The crazy thing is, I didn't realize that 3D printing plastic was so porous. So I'll have to print it a bit better.
so couldn't you use like rubber bearings to keep it from leaking or?
No, the actual, it is the actual plastic. There's an extrusion error right here. So the plastic extrusion got a little porous. So it didn't seal up very well. So it's actually leaking through the
And isn't
plastic
that what
extrusion.
happens when it's not hot enough or it's too hot? Or
There's a lot of reasons you
Yeah.
can get extrusion
Is it,
errors.
remember a long time ago, there was like the whole big thing with the 3D printing guns or whatever. Do you remember that?
Yeah, let's talk about that later. Okay, so how are we doing so far? Are we good? Now, calculating the value of K is just plug and chug. So what you do is you look at all these experiments, look at all of these concentrations, plug in your rate, and get a K value for each experiment and average those 5 K values. Does that make sense? So you got rate equals we don't care times the concentration of this. Plug the values in. Again, anything raised to the 0th power is just 1. So then you're going to get 5 K values, average those K values, and that's going to be your value for K. So can we do that right now? Cool. Let's do that right now.
Did you get that?